Okay, so today I'm going to talk about the OVS eBPF project. In the first of the talk, I'll give a little bit background on this project, and then we'll provide some project updates. Then we'll dive into the Megaflow and the tunnel supports, and we'll share some of our experience on the eBPF development. Okay, so the goal of developing OVS eBPF project is to provide an alternative to the kernel datapath. So the main reason for us to developing this eBPF datapath is because of the maintenance cost when adding a new datapath feature to the kernel datapath. Now imagine we want to add a new feature to the kernel datapath. The first thing that we need to do is to make this method patch to upstream to the NetX tree. And then we are going to backport the feature back into the OVS compatibility code. In order for the OVS compatibility code to be able to support on different kernel version, generally OVS developer will spend a lot of time on making sure the patch can be run on different versions of kernels. And we usually found that it's easy to introduce bug, and also the bugs are not obvious to fix in the compatibility code. So that's motivated us to work on this OVS eBPF project. Okay, so basically what is eBPF? Basically eBPF stands for Extended Berkeley Packet Filter. So it is a way to write a restricted C program and run that in the Linux kernel. So for a kernel that supports eBPF, it will provide a virtual machine that runs eBPF bytecode, and it will also provide the eBPF verifier so that it can make sure that the program that we inserted into kernel are safe to run. We generally rely on the following two mechanisms to develop the eBPF data path. The first one is called eBPF map. Basically, it's an efficient key value storage that resides in the kernel space so that we can use that to share data between the eBPF program and also the user space program. One example of utilizing this mechanism is, for example, the user space OVS vSwitch can install the data path flow by writing that into the eBPF map. And then the eBPF program in the kernel can look up the eBPF map to do, say, a flow lookup. The other mechanism is called helper functions. Basically, helper function is a set of predefined functions for eBPF program to get and push data from and to the kernel. For example, this eBPF helper function can be the map lookup element can be used to look up an element in the eBPF map. Okay, so this eBPF project is actually a continual work that William gave on OVSCon 2016. We have added a whole bunch of new enhancements and also add this new supported feature set and the supported actions. In the following of this talk, we are going to focus on the Megaflow support and also the tunnel support. Okay, so before we jump into the flow lookup in the kernel, in the eBPF data path, first do a quick review on the flow lookup in the kernel data path. So when a packet comes into the ingress, the process will kick in. Basically, we'll use the parser to derive the flow key. And then we use the flow key to do a lookup in the flow table because this is the first packet, so we cannot find any flow in the flow table. So basically, we'll do the kernel data path will do a mix-up code by sending the flow key to the user space OVS vSwitch. Then vSwitch will look up the open flow table in the user space and figure out what's the corresponding data path flow and install the flow into the flow table in the kernel data path. And we'll ask you the action. And for the following packet, since the data path flow is already in the flow table, so we will just do a fast path looking up the flow table in the kernel data path. So similarly, in the eBPF data path, the first thing that we can do is to do the parsing. So the goal for the parser is basically to generate the flow key, which consists of two parts. The first part is the header that we can derive from the packet itself, and also the metadata. So we have the first eBPF program called parser code. Basically, it's a common parser code that can be either attached to the TC hook point or the XDP hook point, which will derive the packet headers. And we have the other eBPF program that can derive the metadata from because it's relying on this two kernel helper function, which is only available in the TC hook point. So we'll derive over there. Then we'll store the flow key into a per-CPU map called per-CPU flow key. And then we will use this BPF key to do a flow lookup in the flow table, but since this is the first packet, so we cannot get any flow, then we'll trigger the opcode eBPF program to forward this packet to the user space. The mechanism that we utilize is the perf event mechanism. So basically, we use this kernel helper to put the key into the perf event map, and then the user space will, the handler thread will pull data from this perf event map and do the flow lookup. So after the flow translation, we'll figure out like which data path flow we are going to install into the eBPF data path. So the first thing we do is the user space vSwitch will first write the rule into the ENC cache. So basically, we implement that by a BPF map called flow table. It is actually a hash table. So the key for this hash table is the flow key, and the action is to output to 2. And suppose this is the corresponding mega flow. So basically for this mega flow, we only care about the first 2 digits of the source IP address and the destination IP address. So the flow key is like this. And we're going to insert that into the mega flow cache, which consists of 2 BPF table. The first one is the flow max. So the flow max is 255.255.0.0, so on and so forth. And also, we have the other eBPF map, which is a mega flow table. This is a hash table, and the key is a mask flow key, and the value is the action, which is output to port 2. Okay, then we will do a downcode. So basically, we'll write the action and also the metadata with this packet into an eBPF map, and we will insert this packet into the eBPF data path. The way we insert a packet into the eBPF data path is we create a tap device, and we attach an eBPF program with this tap device. Then we send this packet into this tap device so that the downcode eBPF program will be triggered. So that's how we put the data back into the eBPF data path. So for the following packet, basically we will use the key in the per CPU flow key, and we look up the ENC cache and the mega flow cache, and then write the action into the other map so that we will execute actions over there. So this is basically how the eBPF data path runs with the mega flow. So now I'm going to hand over to my colleague to talk about the tunneling.
Mm-hmm. Next, I'm going to talk about how eBPF handles the tunnel traffic. First, we will start with the setup. We have 2 hosts, and one installed with OVS empowered by BPF. And we already set up the GRE tunnel between these 2 hosts, and we want these 2 virtual machines, VM0 and VM1, to communicate with each other by the tunnel. And this OVS bridge have 3 ports. The type 0 is used by the VM0, and GRE0 is used by the GRE tunnel, and ETH0 is used to communicate with ETH1. And for each device, we have 2 queues. One is the ingress queue, and another is the egress queue. And we need to attach the BPF code to one of the queues. For the bridge type and the tap type, we need to hook the BPF code to the egress queue. And for other types, we need to hook the BPF code to the ingress code. So let's start with the packet receive. And we want to describe how the BPF handle traffic coming from outside. Let's see, we start from the virtual machine 1. That issue a ping to the virtual machine 0. And when the packet comes from virtual machine 1 and goes through tab 1 and the GRE tunnel, it's encapped by the GRE. And then the Linux kernel will set out the packet from the ETH1. And the packet will go through ETH1 and get to the ETH0 on the local host. And when the packet gets to the local localhost, and it will arrive to the eBPF code on the ETH0. And there is a flow that says if a packet comes from ETH0, and it's a GRE packet with source IP source address from ETH1 to the IP source of bridge 0, then we should deliver this packet to bridge 0. Next, when the bridge 0 receives the packet, it finds the destination of this packet is it itself. So it delivers this packet to local Linux network stack, and then Linux kernel will decap this packet, and because it's a GRE packet, it will deliver this packet to the GRE0 network device. And for the GRE0 network device, when the packet gets to its ingress BPF code, there is a flow that says if GRE0 receives a packet with the tunnel metadata, and its source, IP source is from ETH1, and if it's a RCMP packet from VM1 to VM0, then we deliver this packet to tab 0. Then when the tab 0 receives this packet, it delivers this packet directly to the VM0. So this is the whole process of how BPF handles the packet receive. We can see that the cost of this packet receive is 2 BPF lookups. Next, let's talk about how the BPF handle packet sending. Let's see if VM0 wants to send a RCMP reply back to virtual machine 1, and it will send the packet out to the tab 0's egress queue. And when the tab 0's egress queue gets the packet, there's a BPF flow that says if it receives a packet from tab 0, and it's an RCMP packet from virtual machine 0 to virtual machine 1, and then the interesting part is it sets the tunnel metadata for this packet, and then delivers this packet to GRE0. Next, when GRE0 receives this packet, it encaps the packet with the GRE headers, and then routes the packet to BR0 to transfer. And when the packet gets to the egress queue of BR0, it hits the BPF code, and there is a flow that says if BR0 wants to transfer a packet with want to transfer a GRE packet with the IP address from BR0 to ETH1, then it should deliver this packet to ETH0. Then when ETH0 transfers this packet to ETH1, and the other host will receive the packet, decaps it, and deliver this packet to virtual machine 1. And this is the process how the BPF send a packet through the tunnel. And the cost of this packet send is also 2 BPF lookups. So next, we're going to talk about the lessons we learned during the development process. So BPF program has a lot of limitations that adds to the difficulty during our development. First limitation is instruction limitation. Every BPF program has a 4K instructions limit. This leads to 2 issues. First is we have to break large functions into smaller programs. This smaller program is called a section, and we jump from one section to another by tail calls. And another issue caused by the instruction limitation is we have to limit the number of iterations. For example, in this function called megaflow lookup, we need to iterate through the megaflow in a loop. And the BPF compiler will help us to unroll this loop. And if the loop number is too large, then the produced code will be large and exceed the 4K limitation. So here we can at most have 28 megaflows. If we want more, we have to use the tail codes. Another limitation is the stack size limitation. BPF stack size is only 512 bytes. And to do the operation, we got to put a lot of data structures on the stack. And one of the important data structures is BPF flow key, which is used to look up the flow by BPF. And the size is already 184. And this, because of the stack limit, we can only have 4 bytes in the gleave option. If we get any number larger, like 5 or higher, we will get a stack overflow error. Also, there are verify limitation. One of the limitation is we cannot, sometimes the verify will want to pass if the code logic is too complex. For example, if there are too many conditional statements, too many ifs, then the verify will fail. Another one is we cannot use variable-sized array. So we have to change every TOV into fixed-size array. For example, for the action batch, in the official OVS, it's a variable varied size. But in BPF, we have to use a fixed size. Here we use the 32. And if there are more actions, then we may need like tail calls. And also, if the action number is less than 32, there will be a waste of memory. So in conclusion, we already finished a lot of features in the BPF code for OVS. And right now, we are discussing about the implementation of collection tracking. Right now, we have 3 potential ways. One is we will use the kernel helper support. And the other one is we implement the whole code in the BPF. And the third option is we pump the packets to the user space. All of these 3 ways have their pros and cons. And right now, we are still discussing the way. And we learned a lot of lessons during the process. One is writing large eBPF code is quite difficult because of the limitations mentioned above. And another one is eBPF currently lack debugging tools. So we put a lot of logging in our code to trace the packet and also hex dumps the packet's data. So if anything goes wrong, we can inspect the logs to find out what's happening to the packet. And the third lesson we got is the OVS datapath logic is quite difficult. So it's quite a challenge for us to implement the whole kernel datapath features in the BPF code. Okay, that's all. Thank you. Any questions?
Let's thank our speakers.